Hi everyone, welcome back to class. Today we will be talking about Chapter 10, Choice, Matching, and Self-Control. Now before we start this lecture, I just want to remind everyone that we only have 2 weeks left of class this week and next week. That means that your final exam is coming up soon. So that means you need to go on to the MacEwan website and find when exactly the final exam is, okay? They have already posted those final exam dates and times, I believe, online. So you need to make sure you check that so that you show up on time. Please do not email me asking me when it is. Please check for yourself. Okay, let's get into choice, matching, and self-control. First, what is choice? So usually a choice is considered some kind of cognitive deliberation. And so it's measured based on the effect of different concurrent payoff schedules. So that means there's two payoff schedules happening at the same time. And it's about which one are you going to choose, okay? So with a freedom of choice, then the choices would be unpredictable, meaning that understanding the choices in terms of consequences will allow for prediction. So knowing the consequences of both choices, whether you choose A or B, will help us predict what someone's going to choose. So if we give someone the option of the red pill or the blue pill, if we know that the red pill, say, gives them infinite knowledge and the blue pill gives them gas, most likely people are going to choose the red pill because we know the consequences. But if we don't know what the consequences of the red pill and the blue pill are, then we cannot predict which one people will choose. So understanding these mechanisms of choice is fundamental to understanding behavior because much of what we do is the result of choosing one activity over the other. So why we choose to, say, play in the sandbox instead of the monkey bars. Why we choose to have chicken tenders instead of mac and cheese, that kind of thing. So in chickadees, which I work with in my research, then we put them in an operant box, and they can choose to either go to the feeder or not to go to the feeder. They could choose to do a backflip. They could choose to go drink some water. They could choose to preen themselves. They have lots of options that they can choose. However, we know that the consequences of going to the feeder usually means they get food, and that's something they want, or going to drink some water has a beneficial consequence, whereas doing a backflip doesn't have as much consequences as these other options. So we can kind of predict which behaviors the chickadees will do. So when talking about choice, we also have to be able to measure it then. And the main thing with choice experiments is focusing on this concurrent payoff schedule. So two choices happening at the same time. So our concurrent schedule here is with a pigeon. So in a typical concurrent schedule Skinner experiment, then there's two keys that a pigeon can peck. And it's free to switch from one to the other. So it can choose whichever one it wants. It can stay on B or it can switch back and forth. Doesn't matter. But you'll notice that key A and key B have different schedules of reinforcement. So key A has a variable interval schedule of 60 seconds, whereas key B has a fixed ratio schedule of 10 pecks. Okay, so the pigeon, we can predict which one the pigeon's going to choose at any time based on these schedules, these concurrent schedules, okay? So using your remote for like a TV is also a concurrent schedule, because you can press any number on your remote and receive a different show. And each show, though, has a different schedule of reinforcement. So some channels will have a more interesting show than others. Some channels will have a 30-minute program, whereas others might have a 2-hour program. So those are different schedules of reinforcement. And so having different lengths and different interest levels will affect your watching behavior. So it will affect whether or not you choose one channel over another. You can also choose whether you stay and watch TV or you switch to Netflix. Okay? So understanding these concurrent schedules can help us predict behavior. And we do that using some fun equations. So yes, you will need to know these equations for the final, but remember the final is open book, so you'll be able to use this slide if you need. So how we measure choice is using the relative rate of responding. So this is really behavior. So if we break down this equation, then we've got the BL, so the rate of responding to the left, choice, divided by BL, so the rate of responding to left plus the rate of responding to right. So the rate of responding to left plus the rate of responding to right would be total responding. So the relative rate of responding to the left key here, this is what we're really equating, is the amount of responses to the left divided by the total number of responses. And that tells us the relative rate of responding to the left. And we could switch this and have the numerator be BR, and we'd be able to understand the relative rate of responding to the right key. Now, obviously, this is left and right for the left and right keys, but we could change it to rate of responding to the red versus blue pill, and we just change these little denominators. But it's showing the rate of responding between two choices. But then we've also got the relative rate of reinforcement. So not just the responding, but how each choice is being reinforced. So the equation is pretty much the same. We have the reinforcement for the left key divided by the total reinforcement of left plus right. Okay, so the equations are the same, but they give you different information. So one will predict the rate of reinforcement. If we know the rate of reinforcement, we can predict which key they're going to choose based on which key has the highest reinforcement. But then we can measure and see, did that actually occur by looking at our rate of responding after the experiment. Now, with the rate of responding and rate of reinforcement, we can kind of combine it and use the matching law. So the matching law we got from Herrnstein in 1961. And the matching law is saying that our rate of responding is equal to the rate of reinforcement, okay? Or you can also break it down that the ratio of responding to the left to the right is equal to the ratio of reinforcement of the left to the right, okay? So the relative rates of responding match our relative rates of reinforcement. So why do we have the matching law? Well, it's saying that the proportion of our responding, our choices, is equal to the proportion of reinforcement for doing so. And because there's this correlation between our behavior and the environment, then we can use it to predict future behaviors. So if you know the matching law, and we understand the reinforcements, we can predict responding. So here's the matching law in practice. So this is an example of the matching law. So here on the x-axis, we've got the relative rate of reinforcement of the left key. And on the y-axis, we have the relative rate of responding to the left key. Okay? And what the matching law says is that there should be a positive correlation, an R of 1 between the two. And so here we've got two different pigeons, and we just marked their responding in relation to the reinforcement. And you can see that both of these, I'm just going to insert a fun little line here to show you, here we go, that both of these lines match up almost exactly with this light blue line I just put in. That would be a perfect correlation. So you can see how our experiment with pigeon number 55 and number 231 show that matching law very strongly. Okay? Now here's another example using the matching law. So we've got key 1 is a red key, and the rate of reinforcement is about every 6 minutes, and the response rate is about 75 times per minute. Okay? So we've got our R1 divided by R1 plus R2, so that would be 6 here. And then that's divided by 6 plus the rate of reinforcement for the second key. So key 2, we see our reinforcement rate is a 2. Okay, so we're going to plug that 2 in over here. And so we've got 6 divided by 8. So 6 plus 2 is 8. So that gives us a relative response rate of 0.75. And we can do the same thing with key 2. So we've got R2, which we know is right here about 2 times per minute. So we're going to chuck in a 2, divided by R1 plus R2, which we said was 8. So we've got our 6, which comes from over here, and our 2 that comes from right here. So we've now got 2 divided by 8 is 0.25. So you can see that the relative rate of key 1 plus the relative rate of key 2 equals 1. Okay, that's normal. That's what we want. The relative rates added together should be 1, because remember, these are probabilities. So the probability of the reinforcement rate for key 1 is 75%. The probability of reinforcement rate for key 2 is 25%. That makes sense, right? But now, so that was the reinforcement rate. So that's using this top number here, right there. But what if we use the response rate? So after the experiment, we can use the response rate. So B1 in this instance would be the response rate for key 1. So response rate is about 75. So we're going to put 75 where the B1 is. And that's divided by the total response rate. So that'd be 75 plus our B2. So we're going to move over here. Response rate for key 2 is 25. So 75 plus 25 is 100. So now we've got 75 divided by 100 is 0.75. And notice that this matches our relative response rate. It's almost like the matching law works. What? And then even if we do it with key 2, it's going to turn out the exact same. So our response rate down here and reinforcement rate for key 2 is matched. Same with key 1. Now that is awesome. The matching law works. But is that all that there is? No, there are other things that we need to take into account with the matching law. And so the match law can actually be a little bit more complicated when you take into account new variables like bias and sensitivity. So bias, which is a lowercase b in our equation right here, is a preference for one response or one reinforcer over the others. So it's going to result in more responding on the preferred side and is represented by higher values of bias. So for example, if you're using kids, say in a experiment, and you offer them a red pill or a blue pill, both of which are maybe M&Ms, some kids might have a bias to the color blue. Maybe it's their favorite color, and you didn't ask about this, so you aren't aware that they are biased to selecting blue. So now you've got to take that bias into account when trying to figure out the probability of responding. So notice that our bias is applied to the side of the equation with our relative reinforcement, because the reinforcement we know before the experiment. We know that before people respond. So if we can apply the bias to the reinforcement, we can then properly predict what the responses will be. But we've also got to take into account sensitivity. So sensitivity, which is a lowercase s here, is the the sensitivity of the choice behavior is the relative rate of reinforcement for the response alternatives, or the discriminability of the alternatives when perfect matching occurs. Okay, so if the sensitivity is 1, then a sensitivity of less than 1 indicates reduced sensitivity to the relative rates of reinforcement. So we've got to apply sensitivity. Now, obviously, you might not always know your bias or sensitivity, but these could explain why, if you do your rates of reinforcement and the predictions, but then your rate of respondings come out different, it may be due to either a bias or a sensitivity. And you can actually kind of work backwards then to figure out which one it is using algebra. So is that all that there is? Not necessarily. So the using the sensitivity measures, then we can talk about whether our response and reinforcement rates are either a perfect match. So if an S equals 1 here, then that means there is no sensitivity, and that our relative rates of reinforcement will equal our relative responding with, just the constant of bias. But then we've also got undermatching and overmatching, which are two terms talking about when the S, or the sensitivity variable, does not equal 1. So undermatching, then the S is going to be less than 1. So if the S is, say, 0.5 or 0.2, then that would be undermatching. Overmatching is when our S is greater than 1. So if our S is equal to 2 or 3, that would be overmatching. Now, what do these terms undermatching and overmatching mean? Well, undermatching means that there's reduced sensitivity to the rates of reinforcement, which means maybe someone's just trying everything. It's very common if switching is easy, so there's no cost to switching. So why not try every flavor of or every color of M&M? There's no cost to that, Why should I choose the red one all the time over a blue M&M? I might as well try all of them. And sometimes then this can lead to changeover delay, or COD. And so we'll see an example of this in a minute. The opposite of undermatching would, of course, be overmatching. So overmatching is an increased sensitivity to rates of reinforcement. So this is where someone maybe has the thinking, oh, well, it's best to just stick with one option. So for instance, when I go to the casino, which is fun, I like to play the slots, but I like to stick to just one machine. I don't go through all the different slot machines. I stick with just one. And that's because I want to get the reinforcement from that one machine, and I know that my odds are probably better by sticking with that machine than testing out every single machine. So that actually is a high cost of switching machines, so therefore I do not switch. Okay? Now, what does this look like in action? Well, what that looks like is right here. So in our solid black line and the dotted line, it's just the exact same graph as I showed previously for the perfect matching. So these lines would be an example where the S is equal to 1. Okay, so I'm gonna draw that in right here. So S equals 1. Okay, over matching is over here, and same with under matching. So you can see how over matching and under matching can affect the slope of your line. So with under matching, which is this red line, then you can see that as the rate of reinforcement increases, my responding is not increasing as much. And that's because I'm trying all the different things. Because I want to try all the different reinforcements. So I'm trying not just the left key, but also the right key or the center key. So my responding to the left key is going to decrease or not increase as quickly because I'm trying out that red key, the right key, sorry. With overmatching, which is the green line here, then the opposite is occurring. Here, then, as the relative rate of reinforcement increases, my rate of responding actually increases. So I'm spending more time on the left key, even though the rate of reinforcement might be less down here early on. I'm still sticking to the left key. I'm only responding to the left key. I might try the right key every once in a while, but I'm sticking to that left key as much as possible. I'm not switching up my responses. Okay, so the rate of reinforcement doesn't really affect my responding to that left key. Now, why should we match? Well, the matching law describes the behavior, but it doesn't explain it. So it describes what's occurring. It describes that you're responding to the left key more than the right key or not, but it doesn't really explain why. There's a little bit of theorizing going on with that under matching and over matching, but people are trying to figure out exactly why. So there's two theories about why the matching law works and how it explains the behavior that we're observing. So we've got the maximizing theories and the melioration theories. So the maximizing theories says that organisms distribute their behavior so as to obtain the maximum amount of reinforcement over time. So according to this idea, that animals will actually switch back and forth between response alternatives so as to receive as much reinforcement as possible. And so this can explain the ratio schedule choices. So for a maximum number of reinforcers possible on a VRVI schedule, then participants should concentrate their responses on the VR alternatives and respond only occasionally on the VI component. And actually, college students and pigeons do actually do this. However, they don't actually do this as strongly as the maximizing theory suggests. So while the maximizing theory kind of got it right, the maximizing theory said that we should be doing this type of behavior all the time, but we don't. So an example of this would be a variable ratio, variable schedule would be maybe you have to press a button an average of 10 times, and then you have to press another button. It's available an average of every 2 minutes. Well, you can press the button, so key button A, that has a variable ratio schedule. You can press that button more than 10 times in 2 minutes. You can probably press it like 200 times, right? So you can keep pressing your VR schedule button multiple times and get multiple reinforcements. And then maybe after a while, you'll go over and do button B that gives you a variable interval. But you know that you can get 3 or 4 rewards from button A during the time it takes for button B to kind of, reset. Okay, so you know it takes a while for button B to reset, so you're not even going to bother pushing it again until you've gotten a few rewards from button A. And that's that maximizing behavior. So you're maximizing your rewards by focusing on the VR button that you know will give you a lot of rewards, occasionally going to the I schedule button, but only a few times, because there's no use spending time on that VI button when you can get more rewards from the VR. So if the maximizing theory does not properly explain both human and animal behavior, it doesn't maximize the predictability of behavior, then what else can we look at? And that would be the melioration theory. And so this theory really focuses on the local rates of responding and reinforcement rather than over an entire session. So this theory says that it's about making the situation better than the recent past. So change from one alternative to the next to improve the local rate of reinforcement. So you might change from one button to another because it will improve your local rate of reinforcement. So animals will respond so that the local rate is the same on each alternative. Now, the local rate is calculated over time, so higher than overall rates. So to calculate the entire duration of an experimental session can take a while. So using these local rates is more beneficial to animals. It literally means making something better. So predicts the shifting towards whichever choice alternative provides the better local rate of reinforcement. So the better rate of reinforcement right now. So the maximizing theory was more about how can I maximize my time within this hour-long session? No, the melioration theory says how can I maximize my reinforcement right now? I'm not looking at the overall hour-long session. I'm focusing on right now. And so that better predicts how people will respond. It kind of takes care of the responding rates that are different that we saw in the maximizing theory with pigeons and college students, because people don't always make the best decisions overall, like for a long period of time, when they're focused on just what's best for me right now in this moment. Now, of course, there are some issues. So there's some predicted issue. So behavior is strongly controlled by immediate consequences. And that's what the melioration says. So the matching theory might not be perfectly matched all the way because we're focusing on our immediate behavior, our immediate consequences, rather than the long-term consequences, where the matching law really helps predict long-term consequences. So that's it for this rather long video, but it covers choice and matching. In the next, let's say, 2 videos, then we'll cover self-control.